In this video, I'll be working on problem set 10-6. So we're asked to eliminate the parameter, then write the rectangular equation, and then sketch the curve and adjust the domain if necessary. So for the first equations, x equals t, so that means we can directly plug in x for t, and we're pretty much done there. This is quite easy to sketch. It's going to look like that. The next one, we have x equals negative t squared, y equals t over 3. So for this one, maybe from here we can find that t equals 3y, and therefore x equals, so now plugging that into there, we're going to have x equals negative 3y squared. So our equation is x equals negative 9y squared. And so if you convert this into the standard form for a parabola, you would find that this is a parabola opening left. Okay. Then part C, here we have x equals square root t plus 2 and y equals t minus 1. Now, if I square this, I'm going to get x squared minus 2 equals t. So I can plug that into here and find that y equals x squared minus 3. Okay, so now y equals x squared minus 3, that's a parabola with a vertex at 0, comma, negative 3. However, my domain is going to be restricted because x must be a positive number. X must be greater than 0 based on the first condition, the fact that it's a square root. And therefore, my actual graph is just going to be half of a parabola. Okay? Next question. D, we have x equals 2 cosine theta and y equals 3 sine theta. So if you remember from class, this is an ellipse. And so we're going to want to isolate sine and cosine because sine squared plus cosine squared is 1. And sine is just y over 3. So sine squared is y squared over 3 squared. Cosine squared is x squared over 2 squared. And so this is actually an ellipse, right? So it's an ellipse with x radius 2 and y radius 3. So this is 2, that is 3. All right, so that's what the graph looks like there. Now for question E, it's the same concept, but now we're going to have a translated ellipse. And so from this, we would find that cosine theta equals x minus 2 over 5, and sine theta equals y plus 6 over 4. And so we would conclude from this that sine squared plus cosine squared is 1. So this would be our rectangular equation. And once again, this is an ellipse. Now we do want to be careful, be careful when finding the vertices. So the center is at 2, -6, so it's here. Our x radius is 5, so that's going to go all the way up to here. And then our y radius is 4, so it won't quite reach the x-axis, but it'll go at least up to there. So that's our graph. This question for f. Now we have cotangent and cosecant, so we know it's a hyperbola. X is 3 cotangent theta, and y is 4 cosecant theta. Right? And we have a condition, which is that 0 is less than theta, less than pi. Should say less than, not less than equal to. So that's a typo. But then we're going to use the fact that 1 plus cotangent squared is cosecant squared. Needs to be memorized. And so based on this, you would find that cosecant squared minus cotangent squared is 1. And so cosecant squared is y squared over 4 squared minus cotangent squared, which is x squared over 3 squared, equals 1. And that's a vertical hyperbola, right? So that is a vertical hyperbola. And we do have a restricted domain, so that means we're only going to be looking at one branch of the hyperbola. And now which branch is that? Well, since theta is in quadrants 1 and 2, so theta is in quadrants 1 and 2, which means that that's where sine is always positive, right? So sine theta is always positive, which means that cosecant theta is always positive, which means that y is always positive. Okay, so we can conclude from this that we're only going to be looking at the first branch there, and we should just eliminate this second branch. So that's our answer. Part G, x equals 1 plus cosine theta, y equals 1 plus 2 sine theta. So that's an ellipse. And we should be able to figure out that x minus 1 squared plus y minus 1 squared over 2 squared equals 1. So that's our ellipse. And so our center is going to be at 1, comma 1. And our x radius is 1, while our y radius is 2. So our ellipse will look like that. Right? H looks like another hyperbola. So x is 2 secant theta, and y is tangent theta. And now we have theta, so pi over 2 less than theta less than 3 pi over 2. It's quadrants 2 and 3, right? Okay, so here we want to use the identity 1 plus tangent squared equals secant squared. And so that tells us that secant squared minus tangent squared is 1. And so secant squared is x squared over 2 squared. Tangent squared is y squared. And that should equal what? And that's a horizontal hyperbola, right? So it's a horizontal hyperbola with a equals 2. So I'll have vertices there. And which branch should I keep? Well, I know that for, so theta is in quadrants 2 and 3. which means that cosine theta is always negative, right? Because in quadrants 2 and 3, the x-coordinate must be negative, so cosine theta is negative, which means that secant theta is negative, which means that x is negative, right? So if x is always negative, then we must be looking at the branch on the left, and that would be our answer. Okay, we have x equals e to the negative t, and y equals e to the 3t. So negative t and y equals 3t. Um, you could isolate t. So I'll do it that way. If I isolated t, I could take the logarithm of both sides here. So ln of x equals ln e to the negative t. And then we would conclude that ln x equals negative t. So t equals negative ln x. And then if you plug that into there, we would have y equals e to the negative 3 ln x, which you would simplify based on logarithmic rules, that this is e to the ln x to the negative 3, which simply tells us that, and now we can cancel out the e with the log there, which gives you y equals x to the power of negative 3. However, there is a much easier way to do this. You can just simply look at this equation, and you can pretty much quickly conclude that y equals x to the negative 3, right? And that's just because e to the 3t is equal to e to the negative t to the power of negative 3. You can just multiply those exponents there. So this is fairly easy to deduce. You could also write it as 1 over x cubed. It's easier to understand that way. Now, how is this graphed? You pretty much just have to know how it's graphed. The graph of this function looks like this. It's very similar to 1 over x. However, we also have to look carefully at the domain or range. And that's because an exponential is always positive, right? So x must be greater than 0 and y must be greater than 0. You can think about an exponential graph. No matter what value of t is here, we're always going to get a positive number out of there. And so that means we're only going to be looking at the top right branch of this graph. And that would be our answer there. Okay, next, J. Here we have x equals ln 2t and y equals 2t squared. So we can exponentiate both sides here. So we would have e to the x equals e to the ln 2t, which tells us that t equals 1/2 e to the x. You can just cancel out those there. And then you plug that in here. So y equals 2 times 1/2 e to the x squared. And then you would have 1/2 e to the 2x as your simplified answer from that. Okay, and so that means our rectangular equation is just this exponential function here. And how do we graph that? It's just a very simple exponential curve. Now, are there any domain restrictions? Well, no, because x can be all real numbers, right? No matter what value, well, as long as we were plugging in positive value of t, x can be all real numbers. And so we don't need to eliminate any points here. Lastly, k, we have x equals t cubed and y equals 3 ln t. Probably the best way is to start from the second equation. So we have ln t, it's a bit messy, ln t equals y over 3, and then we can just exponentiate both sides, which tells us that t equals e to the y over 3. Okay, and then we can cube both sides. So x equals t cubed, which is e to the y over 3, to the third power, which is just e to the y. So this is one way of writing our exponential logarithm, sorry, rectangular equation. But we can also take the logarithm of both sides, and we would just get y equals ln x as our answer. And so do we remember the graph of ln of x? Hopefully, Lord willing. It's just this graph here, right? The exponential graph flipped across y equals x. Now, are there any issues with the domain? Well, ln must have a positive t, and so that tells us that x is always positive, but that is true from the graph that we have, right? X is always positive here. But no matter what t is, y can be all real numbers, and indeed, y is all real numbers based on this graph. So the graph looks good, and that is the final answer.